superstring theory, chaos math, advanced algorithm.
Well, hello there, YouTube. How's it going? This is Ali from the AI Enthusiast, and we'll be continuing our linear algebra lecture that we started a couple of days ago, actually. So we'll kind of just basically continue where we left off. We talked last time about matrix multiplication with vectors. Before that, we did like vector multiplication with scalars. We showed that vectors can be multiplied by scalars, then vectors can be multiplied by matrices, vice versa. Matrices can be multiplied by scalars, and then they can be multiplied by vectors. So that was step 4, and you can take a look at it in the description. I have the link to this notebook. But we'll start with multiplication of matrices here. So it turns out you can actually multiply matrices together, and it's pretty straightforward. I import the library, and then I'm doing the random. I'm using NumPy random.randint, generating a matrix that'll have anywhere from 0, 1, 2 numbers. And then you can see over here, it's going to be a dimension 3 by 3. Likewise, I'm choosing numbers between 3 and 6, exclusive on the 6. So it's 3, 4, 5. And then this matrix is going to be 3 by 5. So when I go ahead and do this, you'll see I got these two matrices, A mat and B mat. And then to multiply them, I use NP dot, and that'll give me C mat. So you can see over here, I've got these matrices. And remember, to multiply matrices, just like we were multiplying a matrix by a vector, if you recall here on the top side, you do the row of the matrix and then you multiply it by the column of the vector, which is just this one vector. So it's 1, 2, 0 multiplied by 1, 2, 0, and you do element wise and then you sum it up. So we talked about that briefly. So this way it's going to be 0, 1, 2. That's the row of the first matrix. Then you look at the column of the second one. So 0, 1, 2, 0 times 4, 1 times 5, 2 times 4. And the summation of that, you'll get 13. And then you do 0, 1, 2, the same row, but then the second column. And then you get 13 here. And then you keep doing on this row, you just keep going across. There are 5 columns, so you're going to get 5 numbers across. And then that's for the first row. Then moving on to the second, now you're starting with 102. You're going to transpose it, and you're going to multiply it by this column, all the way for all 5 columns. That's going to get you the second layer of numbers. And then the third row, it's very easy. It's all zeros. So when you multiply by the first column or any of the other 4 columns, you're just going to always get 0. And that's how you do matrix multiplication. Pretty straightforward, and hopefully this is a review for everyone. Just want to get everybody up to speed on some of the pure fundamentals of machine learning and AI. So then let's go to number 6, then identity matrices, and then also multiplying it by a matrix, the identity matrix. So here np.I will give me a matrix of dimensions 3 by 3, and it's going to have 1 across the diagonal. So this is what the identity matrix looks like. If it was a 2 by 2, it would be just 1, 1, 0, 0, and then you wouldn't have this. You can make a 4 by 4, 5 by 5, 100 by 100, whatever you want to do. And here's a random matrix we're generating. Numbers can be between 0 and 9. 3 by 3 right here. And that's matrix A mat here. So let me just run this code. Shift Enter at the same time. And there's my identity matrix. Here's my matrix. And then I'm going to multiply them. So the cool thing about identity matrices is that when you multiply the input matrix and you multiply it with the output matrix, like the identity matrix with any matrix, it's going to give you back the old matrix. And I know that doesn't sound easy to understand. All I'm saying is if I take A mat and I multiply by identity matrix, I'm going to get back A mat. And I can do that like 100 times. I can do that like 1,000 times. I'm still always going to get back the original matrix, 218. You can see 218, 876, 045. We did a multiplication here, resulting matrix, and it's the exact same matrix. This is a really cool concept, but essentially even a vector, if I multiply a vector by this identity matrix, I get back the vector, which is really, really neat. And so this is just a rejog, hopefully a reminder about the identity matrix. And then finally, we have step 7, taking the inverse of a matrix. So step 7 is, and finally, before we actually step 8 and 7, we're going to go over. 9 is a little bit different, but step 7 just shows that we can take the inverse. So here's a general random matrix. Then we're taking the inverse by using this command here, linealgebra.inv. And if it has a matrix inverse, we're going to have it stored in this variable. And then here we can see the resulting matrix. And then, for example, I'm just going to round it. So I'm just going to press enter here. So here's my original matrix. Here's my inverse of the matrix. And now the cool thing about inverses is an inverse of a matrix, when you multiply it by the original matrix, you get back the identity matrix. So I know that's hard, lots being said there, but basically here's the inverse. I multiply it with my AMAT, my regular matrix. Here's the command right here. So AMAT times inverse of MAT. So I multiply these two matrices, and the resulting matrix is right here. And that looks really confusing, but if I round it, because these numbers in the middle in the diagonal, this is the diagonal going here. So that's a 1, that's a 1, that's a 1. They're just ones. And then all these other numbers, they're actually very close to 0. So if you round them, you get back 1, 1, 1, and then negative 0, 0. You can see how this is just a diagonal, and this is an identity matrix. And that's exactly the cool thing that happens when you multiply a matrix by its inverse. And then we're going to real quickly show how you can take the inverse of the identity matrix. So let's make a 10 by 10 matrix, identity matrix, and let's take its inverse. And then let's print it out. And you'll see that the inverse of the identity matrix is itself, which is really, really useful. It's really interesting, right? But it kind of has to be, because the identity matrix by itself, when you multiply by itself, you get back the identity matrix. And if we're saying that, the result is going to be the identity matrix, and then the input to it is an identity matrix, then what you're multiplying by has to be an identity matrix as well. And that's kind of just a side effect of these previous couple of things that we just learned real quickly, or hopefully reviewed. Basically, you're going to get the identity matrix back. And then you can multiply the identity matrix by itself like a million times, and you still get back the identity matrix. So yes, now we have step 9, solve a system of linear equations. So essentially, we've been looking at all these, we've talked about matrices, vectors. We can actually now, what's the so what, right? And so what we can do is we can actually solve systems of linear equations. And I'll just kind of go to this tab real quick. I'm at the studypug.com. So they have a great example here. Here's 3 equations and 3 unknowns. So if you recall from algebra class, and this could have some real world meaning. It could be like a word problem, and from there you derived these equations. And the goal is to find the value of x1, x2, x3. So what you can do here is you can take the coefficients, right? You can take the coefficients. There's a 1 here before the x1. There's a 1 here before the x3. You can take this structure, and you'll see this column is 1, 2, 3 for all the x1 variable. So it's 1, 2, 3, x1, and then it's 3, 2, 1 for x2, and then x3 gets 1, 2, and 1, and that's x3. And then the column on the right is equal to 5, 6, 5. And so that translates to what you can do is on the left-hand side, you can take these 3 columns, the 1, 2, 3, the 3, 2, 1, and the 1, 2, 1, you can combine them into a matrix. And then essentially that is your X, Y, Z, or your X1, X2, or X3. So they kind of show this here below here. So X1, X2, X3, they're just 3 variables. You could call them X, Y, Z. And so right here, you have this matrix, and then you have your resulting vector. And so if you want to show this exact system of equations in the matrix form, here's the actual matrix that we generated. And then the vector we're multiplying by is actually a vector of 3 unknowns, x1, x2, x3, and that's going to equal 5, 6, 5. So remember, matrix multiplication with a vector, it's always just row times and then times the column. So it's the first row times this column, and you'll see 1 times x1 plus 3 times x2 plus 1 times x3, and that's going to give you the first value equals 5. And that is actually just the first equation. 1 times x1 plus 3 times x2 plus 1 times x3 equals 5. So this information over here is encoded by this matrix, or this matrix equation really. And so now there's this thing in linear algebra, you can have a matrix equation of the form AX equals B. So this is A, this is matrix A, X is going to be an unknown vector, and then this is B. And you can actually solve for it using different methods. I'm just going to show you 2 methods that allow you to really quickly spit out the values of these 3 variables. And we're not going to go into the details of having several solutions, etc., etc. I'm just trying to show you a quick and easy way to kind of get a solution to a system equation. And so here's our problem. Here's our equation. And you'll notice I put it into a matrix format here. Here's the matrix. So remember 2, 1, 4. That's the 2, 1, 4. 3, negative 1, and 1 for y. 3, negative 1, and 1. And then 4, 2, and 1. Here we go. Negative 4, 2, and 1 right here. So here's my A matrix. And then my B matrix is my vector, 1, negative 2, and 5. And then what I can do is I can use essentially matrix math. I can multiply. Remember how we can take the inverse of a matrix? And then when you multiply by the inverse, you just get back the identity matrix. So if I had A negative 1, A prime, essentially the inverse of A, and I multiplied it from the left-hand side, that cancels this out. It's just the identity matrix. That's essentially just multiplying. It's like multiplying by 1, really. So if I did that from the left-hand side, I could multiply the inverse of A. I have to do that on the left-hand side. And so I can multiply this B vector. I can do inverse of A times B. And then you'll notice this A cancels out on the left-hand side. And then you're left with the X vector. And you have the result. You have the answer. So there's several ways to do this. This is just an example here that shows how to do this in more detail with practice. So I would definitely take a look at this link. But let me go ahead and show you how it's done in practice. I'm just going to take the inverse of A, and then I'm going to multiply it with B, and that's going to give me the result solution. And so I have the A matrix, the B matrix, and very quickly I know X, Y, and Z. X is negative 4.2, Y is 13.8, and then Z is 8. And that will solve, and basically that'll be a solution to this system of linear equations. I'm just going to do, like as a double check, if this is the right vector, that should be the value of X, then A times this vector should give me the B vector, AX equals B. So this is, we're just saying AX equals B. That's the initial equation, which I don't think I wrote up here, but AX equals B right here, I mentioned it. And so now I'm just going to multiply A by X. I should get back B. So I get 1, negative 2, and 5, and that's what B is, 1, negative 2, and 5. So I can solve for my system of equations. So yeah, that's pretty much it, guys. This is solving a system of linear equations. I need to go over the basics of linear algebra. In the future, if you guys have questions or you want me to dive deeper into these basics, we can definitely do that. But I wanted to show you how we can code this up. And then from here, we'll probably get into some practical videos on how you can manipulate images. Thanks so much. Have a good one, guys. Take care.